Hey guys, it's Mr. Sheeline here. This is the video lecture notes for the Unit 6.3 limiting reactants and also excess reactants with BCA charts. Okay, so before we can get into exactly what the new strategies we're doing here, I want to provide some context and I want you guys to understand what it is exactly that we're doing. So before we do that, before we can know what we're doing and how to do it, we need to know what we're working with here. So what we're working with here is we are trying to determine what a limiting reactant is within a chemical equation, and then what the excess reactant is in a chemical equation. So what is a limiting reactant? Well, pretty much it's a substance in a reaction that just gets used up first. Okay, and once that stuff is used up and it's gone, your reaction will not continue, which means the limiting reactant controls how much of all the product that's made. Okay. This limiting reactant also determines how much of the other reactants are used. So then what's the flip side of this? What's the excess reactant? Well, the excess is just pretty much the substance left over. Okay. Now, let's try to make this into, we're going to try to make this into a picture. But first I want to kind of recap exactly, just real quick. Well, how is a chemical equation set up? Well, remember, a chemical equation is set up like this. You have reactants on one side. Okay, so this would be like A plus B. You have your yield sign, so that's going to be the chemical reaction that's going to combine A and B, and then that's going to produce your product. Okay, so you have reactants over here, you have product over here, and your product in this case would be like AB. So just remember, that's what we're working on here. So what we're looking at, for the most part, is we're trying to determine, in order for AB to be produced, who's my limiting reactant? Is it going to be A or is it going to be B? Who's going to run out first? Okay. So let's maybe now take a look at a picture. Okay, so let's say for the sake of argument that we have a substance, or we're wanting to make a substance, sorry. We're wanting to make the substance here. We want to make this. We want to make Mr. Brown's substance here, and we want to make just one of Mr. Brown's substance. Okay, so that's our product. We want to make this guy. Okay, and we know that in order to make one of these guys, I need to combine 4 pinkies with 2 blue dudes. Okay. So I need 4 pinkies to combine with, need to combine with 2 blue dudes in order to create 1 brown guy. Okay, 1 brown boy. How about that, 1 brown boy? So, I don't mean to, whatever. So, anyway, so I need 4 of these pink dudes, 2 pink dudes in order to make 1 brown dude here. And, but let's say, for the sake of argument, within this, let's say that we only have, I don't know, let's say we only have 1, okay? Let's say we only have 1 blue guy, and let's say we still have 4 of these pink guys. So will we have a reaction? Will we be able to produce 1 brown dude? Okay, this is the minimum. We need to have 2 of these to 4 of these to produce 1 of these. Well, we only have 1 of these, so what we see is that, well, you couldn't have a reaction because our limiting reactant here would be our blue guy, because we need 2 of them, okay? So pretty much that's what we're determining here. So a bit closer to what we're actually going to be working with would be like this. Let's say that we have 8, let's say we have 8 pink guys. And let's say we have 3 blue guys. So when they combine together, will we be able to make 1 brown guy? Okay. The minimum that we need here is 4 pink to 2 blue, and we've got 8 pink to 3 blue. Oops. We have 8 pink. Now we have 8 pink. We need 8 pink to 3 blue here, or we have 8. My goodness, we have 8 pink to 3 blue. How many brown guys are we going to make? So we need, and this is pretty much how it's set up. So all we'd see here is that we're going to use 4 out of here, and then the 2 out of here, And all we can produce here would just be one guy. It'd just be one brown guy here. Okay, now what was used up? Well, 2 of these were used up. We're going to take these 2, we're going to take these 2, we'd have 1 left over here, we'd take 4 of these guys here, and then we would still have 4 left over. Okay, we'd have 4 left over of the pink, we'd have 1 left over of the blue, and we would only be able to produce just this one, this amount of one brown guy. So what would we be determining here is we'd say, well, obviously we could still have another reaction with pink here. We could add, let's say, 1 more blue, and we would get another brown, okay? But the problem is that our limiting reactant here, what's ran out, is my blue here. So because blue ran out and I need more blue, blue is my limiting reactant, okay? So he would be my limiting reactant. While pink here, I still have enough left over to keep going, but because blue is limiting this reactant, this is my excess reactant. Okay. And then we'd say that, well, due to the limitations of blue and how much we have excess of pink here, we were only able to produce 1 brown. Okay. So pretty much that's what we're doing. We're trying to figure out which one is going to be limiting our reaction in hopes that we can measure out everything proportionally so that we can produce the exact amount of product that we want to see at the end of our reaction. That's what we're doing here. Okay. So let's just do this like little concept idea one more time. So still working with pinks and blues here and producing brown guys. So you tell me, okay, you tell me, if we have, let's say, and it's still working with the 4:2 ratio in order to make 1, we're still working with that, right? If I had, let's say I have 12, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if I've got 12 pink guys here, and I have 10 blue guys, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I have 10 blue guys, how many brown guys will I make, and who's going to be my limiting reactant here? Okay. Actually, we're going to make that 12. Let's make it equal. Okay, so 12. So let's say we have 12 of pink, we have 12 of blue. Who's going to be my limiting reactant in this problem, and how many brown dudes am I going to be able to make with these pink and blue guys? Okay, so, and we're still working that we need 4 here to every 2 over here. So let's just think about this real quick. So we need, we're going to be stealing, let's see, so, and maybe this isn't terribly obvious here, but okay, we need 4 here. So we need those 4. We'll need this 4, and we're going to need this 4. Okay, well, we could maybe make 3. We can maybe make 3 here. Let's see if we're able to do that by grouping up. Let's see, we got 2 there. Cool. 2 there. 2 there. Ooh. So it looks like in this case, blue is not going to be our limiting reactant. Interesting, because, again, we only need 4 of these to 2 of these. So we took those 4, and those 2, they combine into 1 brown guy. And then, so that's gone, that's gone. These 4 are used with these 4 for another brown guy. And then these 4 are then used with these 4 to make 3 brown guys. But, look, pink's all used up. We have no pink here, so pink is our limiting reactant. Because, look, blue can still keep going. Blue still has the opportunity to make, let's see, 1, 2, 3 more things. So we'd say here that blue is our excess reactant. Okay? And that ultimately, because of the limitations of our pink guys here, we could only produce 3 brown guys. Okay? So that's what we're doing. More or less. So 10 minutes it took me to do this. Okay, so now what are we doing exactly when it comes to these notes? Like, how does this actually look like on paper. So this is what it looks like on paper. So problem solving using what's called a BCA chart. Okay. Now we have to make sure that we're breaking things up into a particular amount of information. So bear with me here, because this is pretty big. Okay, this is a lot of information. So I'm only going to go through just probably just one problem, and then I'll have a separate video that shows how to do the rest, because I'll want you guys to work on this on your own. So, okay, if there's a reaction, or sorry, that's not what I want to talk about. What I want to talk about is looking at the chart here. So this is the chart that we're going to be using to determine, okay, well, if we start with all of this and we go through the reaction, how much of this will be produced? And out of these two guys, who's the limiting reactant? Okay, who's going to run out first and stop this chemical reaction? Okay, and we're going to use this chart in order to solve that. Okay. So what are those little divvies? So you saw there's the B and then the C and the A. Well, what does B stand for? B stands for before reaction. C stands for the change during reaction. And then A stands for after the reaction. So after it's all said and done, after the dust is settled, what are we left with? Who's going to be our limiting reactant here? Okay. So the before, this is the number of moles given, go on this line. You'll have zeros for the products, okay, because it's before the reaction. Nothing has been added yet. If particles or mass are given, then convert to moles, because we're going to have to work with moles here, okay. Determine the limiting reactant after going through, or determine the limiting reactant. Take the number, and by doing that, we're going to take the number of moles on the before line and divide by a coefficient for each reactant. Whichever is the smallest number is the limiting reactant. Okay. So what exactly does that look like? Because that seems like a whole lot just for this before portion. We still haven't gotten to the change portion yet, and we certainly haven't gotten to the after portion yet either. Okay. So let's maybe just take a look here at, actually, and I'm not going to do just one problem. I'll do two problems. I'm going to do example number 1 and number 3. Okay, so let's just kind of look at this before. So the before tells us that we've got to put down the number of moles given on the line. So we're given moles right out the gate. So if there's a reaction between 10 moles of hydrogen gas and 7 moles of O2, which then creates water, it's asking us what our limiting reactant is. So using this BCA chart here, okay, we've got to figure out what our limiting reactant is. So like it said on the first page, in our before section here, which you can imagine there's like an imaginary line. So imagine there's like an imaginary line across here that looks like this. Okay, that's going to divide everything. So this line's is already here. Okay, it looked like this. We're going to put down the number of moles of hydrogen gas right here, right underneath of it, and then also the number of moles that we started off with O2. How many moles of this do we have? Well, it's before the reaction. We have nothing, 0 over here. Okay, so then what do we do? Well, it says here that if our particle mass is, then it says we've got to determining who the limiting reactant is. Okay, so to know who the limiting reactant is, we need to take the number of moles on the before line right here, and we have to divide by a coefficient for each reactant. So what does it mean by the coefficient? It means right here. What's right here? So what we're going to do here is we're going to say, well, for hydrogen gas, well, yeah, we've got 10 moles of that stuff, and there's 2. Its coefficient's 2, right? And that coefficient is going to give us a 5. Okay, 10 divided by 2 is 5. Okay, remember this is the coefficient from the equation. Okay, so that's 5. O2, let's see, we start with 7, and its coefficient is just 1. Okay, that's my coefficient there. So 7 moles that we started with divided by the 1 coefficient. I divide that and I'll get 7. Okay, so now what do? Well, I'm going to compare. Who's smaller? So clearly the 5 here is going to be smaller, okay? And so because I see that the 5 is smaller, so that means the limiting reactant is H2. Now, you don't always have to write this out. We can simply just do this. Limiting reactant equals H2. So this is how I want these answers to be provided, like this. I just want you to write this so that you have this in the notes. So when you look back, you're like, well, the 5 is smaller, and we got the 5 by using the coefficients and the moles we started with. So that tells me that hydrogen gas is my limiting reactant. So we're going to be able to produce so much, I don't know how much amount of water because this question isn't asking me to find that. Okay. What it is asking me is just to determine the limiting reactant. And I just did that, which was just to see who would run out first. In this case, it looks like my hydrogen gas will run out first. Okay. While my oxygen, I could use a whole lot more here, man. Okay. The oxygen could still keep going. Okay. So then let's look at the change. Okay, let's look at the change in the after. So that's what we do in the before line here. So what happens in the change? So in the change during reaction, this is where we're going to use the coefficient for each reactant and product, then multiply by the number of moles of the limiting reactant. Okay, we're going to multiply by the moles of the limiting reactant. Okay. This will give us the number of moles of reactants used up and the number of moles of the products produced. Okay. So what is that going to look like? Okay, what is that going to look like? Okay. I'm just trying to pace this out. So actually we are going to do a good number of these problems. I keep switching it up, but I guess I forgot that we've got to go through all of these. So let's take a look at number 2, and we're just going to go through the B and the C, and then we'll come back to the A portion of it. So number 2, the most important commercial process for converting nitrogen gas from the air into nitrogen-containing compounds is based on the reaction of N2 and H2 to form ammonia, NH3. How many moles of NH3 can be formed from 3 moles of N2 and 6 moles of H2 given the following balance equation? Okay, so we're going to do what we did before on the before line. So we're going to, like what we did up here, we start with moles, which is awesome. So we can just write these down. So there's 3 moles of N2 and 6 moles of H2. So I've got 3 here, I've got 6 here. Remember, this is before, so I've got nothing over here. And now I have to determine who my limiting reactant is. So I'm going to put N2 down here, H2 down here, and look at that. I've got to now write down the number of moles we're given. So for N2, it's 3 moles. And then for hydrogen, it's 6. That's been given. And now I'm going to look at my coefficients. For nitrogen, it has a coefficient of 1. Put it down there. Hydrogen gas has a coefficient of 3. Put it right there. Okay. And now I divide. So 3 divided by 1 is going to be 3. 6 divided by 3 is going to give me 2. Okay. So my limiting reactant in this case, so my limiting reactant is going to be H2. Now, so this is where the change line comes in. So now what we're going to do is we're going to use this number. Okay, we're going to use this number here in order to multiply the, we're going to multiply the number of, or we're going to multiply this with the coefficient, okay, with the coefficient found in this chemical equation. So it's going to look like this. So I'm going to write this as this is in between the before and change line. So this is what we're doing. We're multiplying 1, because this would be 1, times 2, this guy, right for here. And then for hydrogen, it's going to be 3 times 2. Okay, for over here, it's going to be 2 times 2, because our coefficient for NH3 is 2. Okay. So then real quick, we're going to write down these numbers. So 1 times 2 is 2. Put 2.0. 3 times 2 is going to be 6.0, and then 2 times 2 is going to give me 4.0. Okay, so that's what we're doing here. So now let's backtrack and let's go to the front page and then see what we have to do for the after portion. So for the after portion, we're going to subtract the reactant side amount, so the before and after. So that says that we're going to subtract this from this. Okay, so really what we're doing is this right here. Okay, subtracting this with this. But then on the product side, we're going to add, okay, which would make sense because these two are coming together. They're losing their individuality in order to create a new substance, right? And then this result gives you the amount of moles of each substance left over after the reaction is completed, okay? So let's do that. So 3 minus 2 is going to give us 1.0. That's going to be 1.0 moles. 6 minus 6 is going to give us 0 moles, which is expected for the most part because this is our limiting reactant. And then 0 plus 4 is going to give us 4.0. So the question is, how many moles of NH3 can be formed from 3 moles of N2 and 6 moles of H2? Just 4. So we would say that there are 4 moles, and this would be just fine like this. 4, or actually no, this is how I want it. We would create 4 moles of NH3. This is my answer right here, total answer. Okay, 4 moles of NH3 would be produced. Okay, so let's now put all of that together and let's go through number 3. I want you to work on number 4 all by yourself. I'll make it a separate video of doing just number 4, but let's do number 3 together here. So what mass of H2 is produced from the reaction of 50 grams of magnesium and 75 grams of hydrochloric acid? How many grams of the excess reactant are left over? Okay, so what it's asking is, we're starting with 50 grams of magnesium, 75 grams of hydrochloric acid. When we mix all those together, who's going to be our limiting reactant? And based upon how much of that limiting reactant we have, how much of these two will be made? Okay. So let's figure this out. So here's what stinks about this question, is that we're not given moles right out the gate. We're given grams of magnesium and grams of hydrochloric acid. So if we were to look on the front again, and we were to see that in the before, if particles or mass are given, we have to convert to moles. So because we were given things in mass, we have to convert the mass of magnesium, into moles of magnesium using molar mass, and the 75 grams of hydrochloric acid into moles of hydrochloric acid. So, and we'll do that down here. Okay. So we'll say that we're given 50 grams, not just 50, but 50.0, because we still have to try to keep sig figs here. I'm going to keep sig figs. 50 grams of magnesium, we got to convert that into moles of magnesium. And there's 24.3 grams of magnesium in 1 mole of magnesium. Okay. So when I go through that, okay, now I did say that we've got to keep sig figs. The only place that we would keep sig figs, let's see, would be at the very end when we have to determine the number of grams left over. Okay. Here, in this little thing that I'm about to give you, this is going to be similar to percent yield. We want to keep a pretty large number here. We want this to be exact as possible. So it'd be 2.0576, we'll say, moles of magnesium. Okay. So we'll just keep that for there, just for now. And then we're going to do this. We're going to do the same thing for hydrochloric acid. So 1 mole of hydrochloric acid, I have 36.5 grams, okay, which would give me 2.0548 moles of hydrochloric acid. Okay, so now I've got the moles of my 2 products here. So now I'm going to put this under here, and I'm going to put this under here, because now we have moles of our products. I'm in our reactants here. So this is going to be 2.0576, and then my 2.0548. Okay, so now I've got my number of moles. Well, now what I've got to do is I've got to then divide this by the coefficient. So What's my coefficient of magnesium? It's 1. What's my coefficient of hydrochloric acid? It's 2. So when I do that, I'm going to be left with just 2.0576. But here, I'm going to be left with 1.0274. So my limiting reactant, we would say my limiting reactant here is going to be HCl. Okay. So now what do we do? Well, now we've got to go, oops, and I forgot to put the zeros there. Now we have to, now that we know that hydrochloric acid here, hydrochloric acid is going to be my limiting reactant, we're going to multiply this against all of our coefficients, even on the product side. So it's going to be 1 times the 1.0274, 2 times 1.0274, and over here will be 1 times 1.0274, and then 1 times 1.0274. Okay, so here I'd have just in the change line 1.0274. Over here will be 2.0548. Over here 1.0274 and 1.0274. So remember, we're subtracting here on our reactant side, but we're adding over here on our product side. So 2.0576 minus 1.0274 is going to give me 1.0302. This will give me 0 because it's 2.0548 minus 2.0548. I'm going to add here, so it'll just be 1.0274 and then 1.0274. Okay, now are we done yet? No, because these are just moles. Okay, these are just moles of our product, or sorry, our reactant here of magnesium. This is the mole of magnesium chloride. This is the that's been produced. Here's the number of moles of hydrogen gas that have been produced. So what do we do now? Well, the question is asking ultimately how many grams of excess reactant are left over. Okay. How many grams of excess reactant are left over? Why do my notes not show that? That's weird. Why did I calculate that? Interesting. Huh. Whatever. So the ultimate last question, let's see. Oh, that was our first question. Duh. That's why. We have to first answer this. So what's the mass of H2 hydrogen gas produced? Sorry about that. So we've got to take this guy right here. We're going to take this guy and we are going to convert from moles of hydrogen gas into grams of hydrogen gas. So it'll be 1.0274 moles H2 times the, and we're going to multiply that by the molar mass, which there are 2 grams of hydrogen gas because it's a diatom per 1 mole, which is then going to give us 2.05 grams of H2. So this is where we keep our sig figs. So we start with 3 sig figs, we end with 3 sig figs at the very end here. So there is answering our first question. Second question is how many grams of excess reactant are left over? Okay, how many grams of excess reactant are left over? Well, who's our excess reactant? It's our magnesium. So what we're going to do is just say 1.0302 moles of magnesium. We're going to change that into mass using its molar mass. So there's 24.3 grams of magnesium in 1 mole of magnesium. So those would all cancel out. And what we'd be left with, also keeping sig figs, which would be 3, we would say that there are 25 grams left over of magnesium. So a whole lot going on here, guys. A whole lot going on. So just a quick recap. Quick recap. Okay. So there was a number of different questions in this one little line here. So first we had to determine what was the mass of hydrogen produced. Okay, well we did that. We did that right here. Here's where we did that. Okay, so there was our first question answered. And then the second question was, how many grams of the excess reactant are left over? Where do we see that? Well, that's where we determined it right here. Okay, that's where we determined that. So And before we could even get to all of this down here, we had to fill out our BCA chart. And in order to fill out our BCA chart, we first had to convert grams of our given reactants, turn them into moles of our reactants. We then popped them in. We then looked and then divided by their coefficients in order to get our multiplier, which our multiplier is due to its limiting reactant, which is hydrochloric acid. Put it all together, and then we were able to see that we'd have this amount of moles left over of magnesium. This would be all used up, and we would be able to produce this number of moles for magnesium chloride, this number of moles for hydrogen gas, bada bing, bada boom, and then we find the answer. So, name of the game for this one is making sure that you know that you're answering more than one question in the BCA chart. So in this case, again, our first question was what's the mass of hydrogen produced? Got that right here. Second question, how many grams of excess reactant is left over? And we answer that right here. Okay, so a whole lot going on. So here, I've always said that this thing is not difficult, it's just different. Okay, here we've got both. This is very different and it's pretty difficult. Okay, so we're going to be taking this slow, and I'm going to make sure that you guys understand this. Okay, because we are taking everything up to this point. We are taking everything from Unit 4 and Unit 5, and we're slamming it all together in Unit 6 here in order to say, well, in a real reaction, here's what we start with, how much are we going to end with, what are we left over with? Okay, so I want you to complete number 4 on your own. I'll have a separate video for number 4 where I'll show you how to answer number 4, so I'm not taking any more time here, and you can actually practice one on your own, but I'll have the key. I'll show you how I answer that in a separate video. Other than that, guys, if you still need help, please, 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 if you think that my begging when it came to Unit 5 was bad, I am going to be incessant about this. If you need help, you need to get a hold of me. You need to have conferences on Google Meet if that's necessary. You need to come in on Fridays if you need to, okay? You need to ask me questions like all the flipping time, dude. So you've got to get a hold of me, ask for that help, watch these videos, reference your notes, use all the resources available so that we can get through this and that we can understand exactly how much stuff we're going to be left over with what's put into the system. Okay, so go ahead, give number 4 a whack on your own. Watch the video, the separate video that contains the answer there, and then I will see you guys in the next one.